All right, let's dive into Boolean logic. This is your go-to revision guide to help you absolutely smash your OCR computer science exam. We've taken the best bits from resources by Mr. Wheeler's class, Craig and Dave, and BBC Bitesize to make this as clear as possible.
And yeah, a special shout out to Mr. Wheeler's class. We've designed this explainer just for you guys. We're going to cover everything from the basic gates to the tricky truth tables to make sure you're feeling confident. So let's get right into it.
I mean, have you ever really thought about it? How can a chunk of silicone, which is basically just fancy sand, and a bit of metal, how can that thing actually think or make decisions? It seems impossible, right? Well, to get the answer, we have to go right back to basics.
It all comes down to a really simple idea, a switch. Way back when, computers used these huge, clunky glass tubes called valves. But the real game changer was the invention of the transistor. These are microscopic switches, and we can now cram billions of them onto a single processor, all flicking on and off millions of times a second. It's just incredible.
So, okay, we've got billions of tiny switches. That's great. But how does that turn into playing a game or browsing the web? Well, it all starts with the incredibly simple language that these switches speak. Think about a light switch in your room. It can only be in one of two states, right? It's either on or it's off. That's it. Computers are exactly the same. At their very core, that's all they understand. We just use numbers to represent those states, 1 for on and 0 for off. This two-state system is what we call binary, and it is the fundamental language of every single computer on the planet.
And that's where the transistor comes in. It's the actual physical thing that lets the computer use this binary language. It's the tiny little switch that can be on or off, representing those ones and zeros we just talked about.
Okay, so we've got our language of ones and zeros. Now we need some rules, some grammar, to actually do something useful with it. And that's where logic gates come in. For your exam, you need to know 3 basic ones inside and out.
First up, we have the AND gate. And here's a fantastic little tip to remember what it looks like. Its shape is like a capital D, which, is the last letter of the word and. Super helpful, right?
Now the thing about the AND gate is that it's very strict. It's an all-or-nothing kind of gate. For it to give you a 1 on the output, input A and input B have to both be 1. If even one of them is a 0, the output is going to be 0.
And you can see this perfectly in its truth table. This table just lists every possible thing that can happen. Look down the output column, Q. You can see it's 0, 0, 0, and then finally a 1 on the very last row. And that's because it's the only time when both A and B are 1.
Next up is the OR gate, and this one is a lot more chilled out. And hey, another little memory trick for you. The back of it is curved, kind of like it's helping to make the letter O in OR. So unlike our strict friend, the AND gate, the OR gate is happy as long as at least one of its inputs is a 1. So if input A is on, or input B is on, or hey, even if they're both on, the output will be a 1.
And its truth table shows this really clearly. See? Way more 1s in the output column this time. The only possible way to get a 0 out of an OR gate is if both of the inputs are 0.
And our final basic gate is the NOT gate. Sometimes it's called an inverter, and honestly, it's the simplest of the bunch. It only has one input, and it does exactly what its name says. It just flips the input. If a 1 goes in, a 0 comes out. If a 0 goes in, a 1 comes out. That's literally all there is to it.
Okay, so those are our 3 basic building blocks. But this is where the real magic starts to happen. When we start combining these simple gates together, we can create much more complex circuits that can perform some really powerful logic.
So, take a look at this. Here, we've wired up an AND gate into an OR gate. But now we have 3 inputs to worry about, A, B, and C. So the question is, how on earth do we figure out all the possible outcomes for this?
Don't panic. There's a brilliant little formula for this, and you definitely want to remember this for your exam. It's the 2 to the power of n rule. N is just the number of inputs you have. So in our case, we have 3 inputs, right? So that's 2 to the power of 3. That's 2 times 2 times 2, which equals 8. So our truth table needs 8 rows. Simple.
The biggest trick with these complex circuits is not to get overwhelmed. You just have to work through it logically, one step at a time, from left to right. First, figure out the output for that AND gate.
Then you take that result and just use it as an input for the next gate, the OR gate.
And voila! Here's the finished truth table. By breaking the problem down into smaller, manageable chunks, we can easily figure out the final output for every single one of the 8 possibilities. See? Not so scary when you take it step by step.
All right, you've got the theory. Now let's put it all together and see what this actually looks like in a real OCR exam question.
So, this is a classic exam question. They'll give you a logic diagram. This one's got an AND gate flowing into a NOT gate, and they'll ask you to complete the truth table.
Okay, now it's over to you. This is the perfect time to test yourself. Pause the explainer, get a piece of paper, and see if you can fill out that truth table. Go on, give it a go.
Right then, how did you do? Let's check your answers. The final output column should be 1, 1, 1, and 0. If you got that right, fantastic work. And just as a little bonus fact, this particular combination, an AND gate followed by a NOT gate, is so common it actually has its own special name, a NAND gate. But you'll learn all about that if you take computer science at A-level.
So we've seen how these little gates work and how they combine. But I want to leave you with a bigger question to think about. We know that these gates are the tiny building blocks inside a computer processor, but what are they actually doing? Where are they inside that machine doing all this work to let you watch this, play games, or do your homework? It's something worth thinking about.